I am a huge fan of root cause failure analysis, RCFA, and today I'm going to share a story because there are several really important benefits of root cause analysis that don't often get shared and wouldn't be obvious to you until you've gone through the experience. So I'll start with a story and then share each of these benefits at the end of the video. If you enjoy technical content like this, we invite you to please like and subscribe to our channel. And with that, let's dive into the story. So in this story, I was a young mechanical engineer. I had just recently graduated from school and was at one of my first jobs at a large power plant. And I was assigned a root cause analysis for a chemical metering pump. This pump happened to be injecting a fluid called ETA, ethanolamine, into the boiler feed water system, and that's really important for boiler chemistry to avoid degradation of tubes and metal and things like that. The important part here was I, at that time, like many young engineers, knew a lot about calculus and very little about actual machinery. So in order to do the root cause properly, I had to learn some things. So my first move was to go talk to a senior engineer, and my question to him was, what would you say is a chemical metering pump? And with a friendly eye roll, he said, tell you what, Glenn, let me step you through the types of pumps. There's two big categories. There's centrifugal, there's positive displacement. Chemical metering pumps are a special case of positive displacement pumps. They involve high pressures, low flows. They have a diaphragm that flexes like this, and they're really cool. And here's where you can read up about them. So that was great. That was a good start to my journey. So number two, I needed to disassemble the machine to understand what might have happened internally to cause these failures. So I went to the mechanic, and the mechanic helped me disassemble everything properly and lay it out carefully on the table. And the big thing that I noticed that I thought could be a smoking gun was that the diaphragm itself, which needs to sustain really high pressure, was made of nylon. My gut said that nylon was nowhere near strong enough for a high pressure application like this, and I posited this might be the root cause. So I quickly called the application engineer at the OEM. The application engineer patiently stepped me through the design of the overall pump, but he did validate that, you know what, nylon is actually really strong in tensile strength, Glenn. It's a perfect material for this particular application. It's chemically inert, it has so many virtues, and I'm sorry to tell you, it is the appropriate material choice for this application. So whatever the root cause is, it is something other than that diaphragm. So fair enough, I've tried another thing, I need to find another idea as to what might be going wrong. So the next thing I looked at was the machined faces of the two plates that clamp that Teflon diaphragm into place. I knew that all else equal, concentricity, flatness, roundness, all of these things were important in any precision machine like a positive displacement pump. And I eyeballed the two clamp plates, and they didn't look right. They didn't look concentric. There was a lot of surface roughness, and I thought this might be one of the difficulties that we're having here. So I took those over to a machinist. And the machinist very kindly taught me about fits and dimensional tolerances and things like that, and showed me how to use a dial gauge. It was the first time I had used a dial indicator to understand like very minute displacements across the surface. And so he stepped me through all of the measurements, and we found that it was indeed the case that there was some surface roughness here, and they were slightly out of round, but all of the flaws were less than 3 mils or 3 milli-inches. And for this application, that's really not a problem. Yes, it's imperfect, but it's not enough to cause difficulties with pumping. So I learned a lot, but I had yet another dead end. And I was starting to get nervous that I might not solve my first root cause analysis. So next up, it's a hydraulic system. I went to the hydraulics engineer, and the hydraulics engineer explained to me that in systems like this, by definition, you're generating a lot of pulsations. You have an inlet check valve and a discharge check valve, and you have a diaphragm that's oil back, that's kind of pivoting like this. And in doing so, inevitably, you're going to be creating pulsations inside of the line, and that you want to make sure that you dampen those out. And sure enough, this line didn't have any type of pulsation dampening on it. And he also showed me a little trick involving a gauge that could show the presence or absence of pulsations, and they were there for sure. So we went ahead, we sized a pulsation dampener and had it installed into the system. This was great practice. It no doubt prevented future failures, but it was still not the root cause of what was happening. So finally, there's only one other component that could plausibly have an impact on this pump's reliability, and so I disassembled that. Those were the inlet and the discharge check valves. If you think about a positive displacement pump, on the suction stroke, when it's sucking a fluid in, it's going to need a check valve that will open up only so that you can suck in. And then on the discharge stroke, you're going to want that valve to close really firmly, and you're going to want the discharge valve to open under high pressure and then inject into the feed water in this case. And so both of those have an important function, and when I disassembled them, I was super happy to see a whole lot of black goo inside of both of them, caked over all of the components. I had no idea what the black goo was, but I was smart enough to know that that wasn't normal and that was not desirable. So the way the story ends, I looked at the materials that were used for the O-rings inside of the check valve, and we were using Viton O-rings. Viton is actually a fantastic O-ring material for 98% of the applications out there in the world. One exception is ethanolamine, ETA, the exact fluid we happen to be pumping here. It turns out that ethanolamine eats Viton alive and causes it to degrade into a black goo of death, which is exactly what I found inside of those check valves. So finally, we had reached root cause. The fix in this case was a relatively simple design change. All we had to do is change the material, not the dimensions of the O-ring, so nothing changed except for the material of the O-ring. We decided on Teflon O-rings, plenty strong enough for the application and plenty chemical inert with an interface with ETA, and everything went well. We put in the Teflon O-rings, we installed it into service, and the pump began operating properly and didn't lose its discharge head for the foreseeable future. And so that's the end of that particular story, which was a really big win. But the point of this story, although that's a really interesting technical root cause, I wanted to sing the praises of root cause analysis in general beyond its ability to solve a specific technical problem. Now, in telling this story, I made it into a narrative that slightly simplified what actually happened. Each of those folks that I spoke with were actually interacting with me on a regular basis and were contributing their expertise into the root cause team. And so benefit number one is learnings. Independent of the fact that you actually solved the problem and so learned how to fix that, you have an enormous amount of cross-functional learnings when you do this. Myself as the young engineer in this narrative, I learned from literally everybody at the table, but the same applied to them. We had a machinist, a hydraulics engineer, a senior mechanical engineer, an OEM from the pump manufacturer, who did I miss? A mechanic that was doing all the disassemblies. Each of these people was sharing their expertise as they went through their piece of the puzzle and intently listening to everyone else around the table as we discussed what could plausibly go wrong with a pump like this. And so tremendous amount of cross-functional learnings is the first benefit. Even if we hadn't solved that first problem, which thankfully we did, every one of us learned a ton that we would then bring to whatever the next problem is that we faced. Number two, team camaraderie. Team camaraderie and team morale is a really important thing in the production environment. Any of us that have worked on a production floor, be it at a process plant or a manufacturing plant, we know that life is stressful there. You always have production goals that you have to hit. When you want to fix a machine, you always have too small of a window to be able to do that. And when you want to research things or install new equipment, you always have less funding that you would actually want to get the job done. It's just a fundamentally stressful environment. As a result, it can be a huge boost in morale when you have multiple cross-functional people around the team working together to solve a problem. The team camaraderie that you get out of that is really substantial. The only warning that I'll say is if your team is prone to finger pointing, if there's any vibe at all within the root cause team that says, we're gonna find which department is responsible for this so that they can be held accountable and we'll make sure that this never happens again. Accountability is a good thing, finger pointing is not. And you know the difference in vibe when you're there in the room. And so my advice would be ensure that you don't have the finger pointing vibe. Accountability is great, it's very different from finger pointing and underbus throwing. Make sure you don't have that, otherwise you don't get the full benefits of the root cause analysis. And then a final benefit is actually personal. It's individual morale. So for me personally, the win that I got out of actually solving this problem that really mattered to the production team and that really impacted the business, that was huge. It was at least 100 times larger than anything resembling Ice Cream Fridays, Taco Tuesdays, free bowling night. All of that stuff is great and I encourage you to do it. But for me at least, and I think for the vast majority of manufacturing employees, simply getting a win, doing a good job, and really impacting the business in a positive way, that is the #1 booster of morale. And so that's why I wanted to share this story. It happens to be an interesting mini lesson on chemical metering pumps and positive displacement pumps. But more importantly, I want to share that root cause analysis has 3 huge benefits beyond solving the actual problem that you're looking at. And those are learnings, team morale, and individual person morale. So I strongly encourage everyone to take on a root cause failure analysis program. It's one of my favorite things to engage in on the factory floor, and I hope you'll do the same. Thank you so much. If you enjoyed this content, as always, we invite you to like and subscribe and can't wait to see you on the next video.